jump in and drop your questions on me. So yeah, about me, I'm Bob Wold. Nice job calling it out, guys. I've been blown away with how good you guys are at information discovery. A little bit about me. I've spent 25 years in industry. I'm the founder of a traditional quantum startup called Quantum Rings, which is, very much like a, I don't like I almost want to say like, real world traditional startup, although like the real world is way less exciting than, the world that we all live in here, to be honest. I've always been a deep tech enthusiast. I've also been like a massive skeptic, and I was a huge skeptic of crypto in general, which sort of, I will say, started me off kind of assuming that this journey was going to be sort of a quick little dip your toe into, the exciting world of crypto. But man, I decided I want to dive in head first. This is great. We're based in Boulder, Colorado, and some people have asked about the logo. That's totally the Boulder Flatirons. So if you guys like Google Boulder Flatirons, it's like a distinctive mountain range right by Boulder. And I go by Beyond Nisk. All right, so enough about me. Oh yeah, the one thing about me, I've got, I am bullish on this market now. So why quantum? Well, quantum holds the promise to transform the world. That's like a super hypey thing. We'll have to dive into figuring out what that actually means. But Crux was actually onto it at the beginning, which is basically that like traditional computers are limited by how much information you can encode into them, like how far you can search within a search space. Quantum computers have this crazy thing where you can like encode the constraints physically into a computer, and it can represent all possible states in a space simultaneously. And so what that basically does is it can be applied to a specific set of problems that are like super big problems, super valuable problems that hold the promise to transform the world. And so like when I tell people about this in my day job, I focus on the fact that my grandchildren hopefully will live in a world where we've discovered cures to the most harsh illnesses. We can potentially cure AIDS, potentially cure cancer, because real-time computational simulation of new drugs will be enabled, where you don't think necessarily about how far you can get on your EV charge, because we've discovered better batteries that can charge faster, hold more energy, that have a lower impact on the earth to mine them, where we're no longer faced with like just the goods that are produced not being with the people that need them, because we can optimize supply chains, where today we have to approximate those optimizations because of computational limitations, or worlds where everybody's 401k looks a lot bigger because portfolios are being optimized. And it's not just sort of a directional promise. McKinsey did a study where they actually looked at each of these problems and experts in each of these fields and mapped the specific problems with the market that they were going to create and with the functionality of quantum computing and quantum algorithms. And they estimated that the first market's a $400 billion market. In the materials space, you have a $500 billion market, $600 billion in logistics, and $600 billion in finance. Now, I sort of misquoted that. It's not a market, that's the economic value creation by solving these problems, meaning that, we're unlocking by 2035, potentially $2 trillion in economic value if quantum computers can hold their trajectory, which is pretty damn exciting. And so, I'm hoping, Const, you're feeling good right now? Are you feeling bullish?
I am. But how does it all connect to Bittensor, though? This is the big question.
Yeah. All right. Let's get there. But well, before we do though, I just gave you like the peachy story. So let me also tell you the real side of it too. And then let's connect in Bittensor. So you're like, okay, well, if you can do all this awesome stuff, you're going to totally revolutionize the world. Then why didn't you just cure cancer already? Right? Let's do it. Let's go. Well, it turns out that quantum computers are really, really hard because they require you to isolate physics and stop them from physicking with the rest of the world, right? And so that's why you see these things in these giant super refrigerators that get down to 0 Kelvin, right? Physics are very hard, and so in the real world there are very few of these computers, so you got to wait in line. They're super noisy and error prone, and they cost gobs and gobs of money. And so to put some numbers on those, I have to wait hours or days for quantum computer. Like yesterday, I had to wait 12 hours to run on IBM's quantum computer, and that's not abnormal. It's not like that was a long wait time. They have huge error rates between 0.1% to 1% per operation. So that's not per program. That's like essentially per line of code in the quantum world. And they cost, if you think GPUs are expensive at like $2 to $4 an hour, try spending, $5,000 to $15,000 per hour on them. And so if you're the people saying like, oh man, I'm going to go solve these billion-dollar problems and transform the worlds, you are blocked, right? You're sort of stuck by this. So maybe you're not feeling quite as bullish anymore. No, it's still good. It's still good. So the people that know kind of know that there's two sides to this story. And so if you look at like Jensen, CEO of NVIDIA, he'll talk about how exciting it is because they're going to solve these exponential problems like simulating atoms and molecules for drug discovery. You're just going to need several million physical qubits. Or you can look at Sundar from Google, and he'll say, yeah, we're going to totally learn the basic structure of molecules that we're sort of missing today, except you're going to need a totally fault-tolerant quantum computer to do it. Still a bull. Or Satya from Microsoft, who talks about, lossless power grids, carbon capture from atmosphere, quantum computers so powerful we can model nature itself. Totally a bull. And so like all of these guys are equal parts like excited and not excited about it. Or they're excited, but they're realists about it. But the cool thing is that, and this is sort of tying into why Bittensor, you guys probably are super familiar with AlexNet. I probably don't need to explain that to this audience, but just in case, in 2012, AlexNet was released and it kind of blew people away with how accurate that model was. And then once they put that model out there and everybody else started working on this problem and really democratizing it, thousands of smart people trying to do better, you can see that in the 7 years that followed, you could get AlexNet performance with 44 times less compute. And that's freaking awesome because lots of smart people working on these problems get you to innovation. Well, history is kind of like starting to repeat itself in that if you take a look at some of the really exciting quantum things, like, okay, in this case, those RSA ones are around breaking encryption. FOMOCO is about, simulating like a very important molecule. There are these different quantum algorithms. You can see that how big a quantum computer is going to have to be to solve these algorithms is getting better because the scientific community that's working on them is making the algos more efficient. You can also see that quantum computers are getting better, like the qubits themselves are getting better. This particular chart happens to be from Google's, Google's Willow processor. This is about coherence times of qubits, which, one of the users on Twitter had asked us about coherence times. They're getting better, error rates are getting better, error correction's getting better. All the charts are in the right direction. And so when I think about that, I was reminded of this DARPA slide from the DARPA QBI conference that I was at in DC in February, where they put up this chart of like all the different quantum problems scatter plotted across the size of quantum computers on the bottom and the number of quantum operations. And so you can sort of see that like some problems are going to require huge numbers of qubits. Some are going to require just a few qubits. But the cool thing is that the quantum computers are getting better and we have these problems getting easier. And so the conditions are sort of like just right for this thing to go to the moon. Okay, this isn't like like to the moon. Maybe it's make no financial projections, but I mean like quantum is ready to go to the moon, right? The problem is going to be that scarcity is going to remain. And I literally was talking to the number 2 quantum computing company in terms of logical qubits, and I asked them, how much is it going to cost to buy one of these quantum computers? He says, I can sell them for N million dollars. And I'm like, that's awesome. How much is it going to cost when you have 100 logical qubits? And he said, I'm not going to sell them when I have 100 logical qubits, because once I have 100 logical qubits, I'm going to solve the world's, like these handful billion-dollar problems. The only way people are getting access to them is we're co-developing IP. And so power and scarcity make people do strange things, right? And I think that's like what the quantum world is like, even when it's bad for everybody in the end. And so that is why Bittensor.